This one is problem 1.20. In this problem it says that there are two balls kept on top of each other inside a can, and based on their weights and size given, we need to check whether this can is going to tip over or not. Okay, so from the basic understanding, when we are looking at tipping here, the configuration is such that this tipping will happen this way. Okay, and for tipping, what is important for us to see is what is happening at these two contact points. Okay, and at these two contact points, if there are these normal reactions here, as soon as the tipping will happen, this normal reaction right here will become 0. So that's the basic idea around which we are going to develop this problem. Okay, so now in analyzing the forces and all other things, let's first consider two of these balls as a system first and try to draw the forces on these. So if there's a contact here, there will be a horizontal reaction coming on this ball here, another one coming here, another one coming there. Now let's name these balls. I'll call this one as ball number 1 and this one as ball number 2 here, and there will be weight acting downwards, weight acting downwards here. Now if this is 1, I'll call this R1x, R1y, R2x, and since both of them have same weight, I'll call this WB and WB. If I do the force and movement balance for this system right now, in the x direction I can see that R1x has to be R2x because these are the only two forces. R1y need to balance the weight of two balls, so this needs to be WB times 2. And for the moment, I can take the moment at about this point here, so that R1x, R1y and WB, all of this will not contribute to the moment. Now this one right here will be WB times the horizontal distance, let's call that Lx, and the vertical distance right here, let's call that Ly. So WB times Lx, this is going to be a clockwise movement and needs to be balanced by R2x times Ly, which is counterclockwise. So from this we can figure out R2x is nothing but WB Lx over Ly. We'll see later what are these values of Lx and Ly. So this is what we are getting from the free body diagram of these two balls put together. Now let's separate this can out and see what are the forces on the can. So let's assume that the can is not tipping. Okay, and in case the value of n here either comes to be 0 or it goes negative, that means the solution is not feasible and the can is going to tip over. So at the bottom there are these two contact points, so it will have two normal reactions, n1 and n2, and because of the orientation of balls, this normal reaction is not going to be same, so that's why I am naming them n1 and n2. The contact with the first ball, if R1x on the ball is on the right hand side, this R1x is going to be to the left on the can. Similarly, this R2x is going to be going to the right on the can. In addition to this, right through the center line, there will be this weight of can WC acting. Okay, and this we have noticed earlier also, and this distance right here is Ly. Now again, if we do the force balance in the x direction, we don't get anything extra here, R1x equal to R2x, which we have seen earlier. For the y direction, we get n1 plus n2 will be equals to WC. Now for the moment, we can take moment about this right bottom point so that n1 appears in the equation. So now if I do that, let's mark this right here as capital D, which is the diameter of the can. Okay, and this one right here, this distance right here is going to be D by 2, which is equal to this one right here, half of the diameter of the ball. So D is the diameter of the can and small d is the diameter of the ball. So now if you do the movement balance about this point, n1 times capital D will be a clockwise movement about this point, minus R1x times small d by 2 will be an anti-clockwise movement about this point, minus WC times capital D by 2 is going to be again anti-clockwise, and plus R2X times total distance from here to here is going to be Ly plus D over 2 equals to 0. Now if you recall, R1X and R2X, these are same coming from this equation, so this D by 2 term will cancel out with this term. From here we can see that your N1 value, if I move all the terms to the right hand side, it's going to be WC by 2. If this D cancels out with this D, I'll divide this by D here, minus R2X Ly divided by D. So tipping will happen if your N1 value less than equals to 0. Now let us simplify the expression for N1. So N1 is equals to WC divided by 2 minus R2X Ly. Now if you look at this equation right here, R2X Ly can be written as WB Lx, this divided by D. Now Lx value, which is this one right here, if this distance is capital D, and this one right here and this one right here, this is going to be half the diameter of the ball, and this one right here is Lx. So we can write down capital D equals to 2 times half the diameter of the balls plus Lx. That means your Lx is nothing but capital D minus small d. So your N1 now can be written as WC divided by 2 minus WB capital D minus small d divided by capital D, which is WC divided by 2 minus WB 1 minus D over capital D. Now there are two sets given in the problem, and in both the sets, if you notice, there is no difference in the values for the ball in terms of weight and diameter, only the can is changing, right? So if you look at your first set, your N1 value is going to come from WC, which is the can's weight, 0.57 divided by 2 minus WB, which is this one right here, so 2, 1 minus small d is 45 mm and capital D is 50 mm. Okay. Similarly for the second set, your N1 value is 1 Newton is your can's weight, minus W remains the same, small d remains the same, and your capital D becomes 70. So if I solve for N1 in this case, it comes out to be 0.085, and in this case it comes out as minus 0.21. So in this case, since N1 is positive, so there is no tipping happening here, we still have the contact, and in this case the can is going to tip over and it's going to lose contact. So that's how we do this problem.